everyone. Today we will discuss some next questions. Question number 6 is define overfitting and underfitting in the context of machine learning models. Describe how these issues can be identified and list strategies to prevent or mitigate them. What is overfitting? Overfitting occurs when a machine learning model learns the noise and random fluctuations in the training data instead of the true underlying patterns. So, under overfitting occurs when the model learns too much details from the data. So, the characteristics are the model is overly complex, too many parameters related to data size. The model performs very well on training data but poorly on test data and validation data. The third one is the decision boundary becomes too specific and irregular. Now, the example is in polynomial regression, a 10-degree polynomial may perfectly fit training points but generalize poorly. So, what is underfitting? Underfitting occurs when a model is too simple to capture the underlying patterns in the data. So, its characteristics are model performs poorly on both training and test data, and the model fails to learn the important relationships in the dataset. Third one is insufficient model complexity or too much regularization. An example is a linear model used for non-linear data patterns will underfit. Okay, identify overfitting and underfitting using learning curves. Plot training accuracy error and validation accuracy error versus training size or approaches. Okay, so what are the signs of overfitting and underfitting? मेट्रिक बिहेवियर ट्रेनिंग एरर बहुत कम होता है वैलिडेशन टेस्ट हाई होता है और गैप क्या होता है लार्ज गैप बिटवीन ट्रेनिंग एंड वैलिडेशन एरर ओके देन वी विल डिस्कस साइन ऑफ अंडरफिटिंग ट्रेनिंग एरर ज़्यादा होता है वैलिडेशन टेस्ट एरर हाई होता है गैप स्मॉल गैप बहुत बेटर so what are cross validation it performance varies greatly across faults overfitting. Okay, so overfitting is if performance varies greatly across faults. We discuss before that faults are the small parts. Okay, so if their performance varies very greatly, then it's called overfitting. Now, if performance is consistently low across faults, it's called underfitting. Now we'll discuss bias variance behavior. In overfitting, variance is high but low bias. In underfitting, high bias but low variance. Okay, now performance comparison. Compare training accuracy with test accuracy. Large gap है, it means overfitting. Both low है, इसका मतलब underfitting. Now the third one is strategies to prevent or mitigate overfitting. Below are common techniques grouped by approach. Reduce model complexity, use a simpler model, reduces decision tree depth. Now, regularization. Add a penalty for large model weights. Its types are L1 regularization, L2 regularization, elastic net, dropout. So, what is L1 regularization? It encourages sparsity, set some weight to zero. Uh, and L2 regularization shrinks weight smoothly, and elastic net is the combination of both L1 and L2. And what is dropout? It randomly remove neurons during training. Now the third one, data related strategies. First, increase training data. It helps the model to generalize better. Second, techniques like data augmentation are used in images. Add noise to training data. Make the model more robust. Early stopping for iterative learners like neural networks of gradient boosting. Stop training when validation performs stops improving. Now cross validation. It ensures model generalization generalizes across different subsets of data. Now strategies to prevent or mitigate or underfitting. It increases model complexity, It uses more powerful model, add more layer neurons in neural network. It also uses high degree polynomial if appropriate, and it reduces regularization. Reduce regularization, decrease L1 or L2 regularization, reduce dropout rate, add more features, feature engineering, bring in more relevant variables, D, train longer, especially for neural networks. Insufficient training time may lead to underfitting. Reduce noise in data. Clean the dataset. If we clean the dataset, then obviously the noise will automatically reduce. Handle missing values appropriately. Now we will discuss seventh question. It is differentiate logistic regression and linear regression on the basis of hypothesis, parameters, and cost functions. How gradient descent algorithm is used to optimize the parameters. Difference between logistic and linear regression. On the basis of hypothesis function, here is the function of linear regression and logistic regression. And the nature of hypothesis output in linear regression is always produce continuous values. But in logistic regression, it always produce probability between 0 and 1. Parameters. Parameters theta 0, theta 1 up to theta n represent direct contribution to predicted value. In logistic regression, same parameters theta 1, theta 0, theta 1 to up to theta n, but represent contribution to log odds of the class. Cost function, mean squared error has the formula, and log loss cross entropy has the formula. The shape of cost function, convex for parabola shape here, and in logistic regression, convex for logistic regression. Now, how gradient descent is used to optimize parameters. Gradient descent is an iterative optimization algorithm used to minimize the cost function by adjusting the parameters. Now, general update rule. Here is this formula, and here alpha is learning rate, and these are gradient slope of with respect to parameter. It's update because you move downhill on the cost curve. Gradient descent for linear regression. Here is the gradient of MSE formula and parameter update formula. See, gradient descent for logistic regression, gradient for log loss. Here is the formula. What we noticed that the same gradient form, but h theta x is a sigmoid output, not linear. Okay, parameter update. And here is the formula. Now, question number 8. Write a program in Python to implement logistic regression and linear regression. For every method, compute and display the implemented model's evaluation measures such as accuracy and other values of different evaluation metrics such as confusion matrix, accuracy, precision, recall, F1 score, specificity, and loss function, RMSE, and R2 score. So here is the complete Python program. Here is the program for linear regression. Firstly, we will declare a class linear regression, and here we are initializing a constructor, and we are making a function fit name, and we are making a loop here and a predict function there. Here is the program for logistic regression also. Here we are also initializing a constructor, then we are making a function sigmoid, then we are again making a function fit. Now we are using a loop, and here is the part 1, linear regression evaluation matrix. So here it will print linear regression results. Here we will be seeing the results. Okay, evaluation matrix, I'm assuming. Okay, this is the output, and part 2 logistic regression evaluation. And this is for logistic regression. Okay, now we will discuss question 9. Write one hot encoding for the given data. One hot encoding idea. One hot encoding converts the categorical column fruit into binary indicator columns. Okay, one column per category. Here the categories are apple, mango, and orange. We create three columns: fruit apple, fruit mango, fruit orange. Each row gets a 1 in the column for its fruit and 0 elsewhere. Result: one hot encoding table. Okay, so here we are writing the results. We are also having a column value of fruit, price, and fruit apple, fruit mango, fruit orange. Okay, so how much apple we are having in the first row? One apple. Mango, one, and apple, one. Okay, this is the standard one. If you want to avoid collinearity in a linear model, you can drop one column. Example, keep only fruit apple and fruit mango and infer orange when both are 0. Value of fruit appears numeric and redundant with categories. Apple is 1, mango is equal to 2, orange equal to 3. If value of fruit is the simply an encoded form of fruit, you normally either use the one hot or numeric encoding, not both. Now, why KNN is considered as a lazy learning? Discuss K nearest neighbors. Consider the following table. It consists of height, age, and weight value for 10 people. The weight value of ID 11 is missing here. Predict the weight of this person based on their height and why Canon is considered as lazy learning. First, no model building step. During training, KNN only stores the feature vectors and labels of the training example. There is no parameter fitting or creation of a compact predicting model. Computation is default. All heavy computation, computing distances, sorting neighbors, aggregating targets, happen at prediction time when a query instance arrives. Now, contrast with eager learners. Methods like linear regression or neural network perform training to compute parameters, weights before prediction time. Predictions are then cheap. KNN delays this work and is therefore called lazy. Practical implications. Training is fast, but prediction can be slow. Memory intensive for large datasets. Also, Cannon's behavior depend heavily on feature scaling and choice of A. Okay, so now we will compute the value of ID level. So, firstly, given a query point xqx, qxq compute distance d q xq xi. Okay, so we will find out the distances. Okay, using Euclidean distances. Select the KKK points with the smallest distance. Predict the target is. Here is the uniform average formula and distance weighted average. Numerical prediction for ID 11. Height is 5.5 and age is 38. We compute results both without scaling. Row Okay, here we didn't use Euclidean formula and with standardization. Standardization is recommended. Given training data is here, for ID 11 we find out the answer. Height is 5.5 and age is 38. Okay, here is the standardized distance to ID 11 and we can compute Z by this formula. Thank you.